Okay, let us continue. So we have one solutions. Okay, this is an equation 2, but another one we have a solutions like this. Okay, so you have your f x y z, for example. This will be given in terms of what do you have just now? A sine kx plus maybe you put and b cos kx. Alright, okay, so if you look at example page 629. Okay, so once so I put here r, because r here can be x, y, z. So if you look at example page 629, example 1, so the problem is in one dimensions. Okay, in one dimensions, so you have here only respect to df dx squared. Alright, so in this case then your solution would be correspond to two option. You have sine kx and then you have cos kx. Okay, alright, and then notice that your functions of t, the solutions is exponential. So this is always exponential k square alpha square t. Okay, look back from equation 2. Okay, so in a way that remember your u solutions for this heat equation is given by multiplications of functions f and t. So this is none other than, so if we follow the books, you can just exponential k square alpha square t sine kx, and another one exponential k square alpha square t, and then you have cos kx. Okay, then the rest follow. So this will be a very general solutions. So if you want to go for exact solution, so what do? Then you apply the boundary value problem. Okay, alright, so if this is the case, okay, so one must or need to determine k. Okay, so that's why in your problem, okay, you have your u in the solutions. This is the correct n pi alpha over l squared t, and then sine n pi x l. Okay, so where do this l come from? Okay, it comes from this, the fact that you have this, consider the model, the problems that you're considering. You have a distance of l here with y, and you're trying to find the heat flow to a slab. So these are slab with thickness l. So all the parameter, so alpha l are parameter for the problem. Okay, alright, let's try to look at another equations. Okay, this is a simple one, you have done this before. We look at the Schrodinger equation. So over here, alright, okay, so what we have for the Schrodinger equations, so the solutions that you assume is psi, so you have phi x, y, z, and then you have functions of t. Okay, so it's a partial derivative, again it's a PDE, okay, and your Schrodinger equations takes the form minus, you have a reduced Planck constant, and then you have phi plus v, okay, and then you have h1 over t dt. So this actually equivalent by E, and you notice that these are stationary solution. Okay, your Schrodinger equation actually takes the following. Okay, alright, this is the original. You see there is a partial derivative of your psi respect to t, but if you substitute, you arrive at, so I give you, this is equation 1, this is equation 2, sorry, this is equation 1, 2 and 1 and 2, okay. So you look, these are actually both, okay, this equals to E some constant, this also equals to E some constant. You can solve for t first. So what do you get? So what's left is just so you integrate both sides. But then you have t, this is none other than, and you have some exponential IH h E T. Okay, over here, sorry, you have minus sign because it become minus IH bar. So this is not correct. Let me rework this again. So you have I E dt IH bar. Okay, integrate both sides. You can have you get minus I E t over h bar. Okay, so your t exponential minus I E t over h bar. So your E here will be arise as a parameter that you must compute. Okay, and then if you look at the solutions, okay, so let's say for the stationary, this is none other than time independent Schrodinger equation. Okay, so you have h bar square 2m d phi d x square over e phi. Okay, alright, or you can always clean this equation, dx square plus 2m e over h bar phi equals to 0. And you can also introduce your d square equals to d dx. So you have d plus square 2me over h bar. So all these multiply with the phi equals to 0. So can you find me the solutions, finding the roots here? Okay, finding roots. So what do you get? So you have d square equals to minus 2me h bar square and your d is plus minus I to me square root over h. Alright, okay, so in the book they substitute your k square equivalent to me over h bar square. So then you can also have, okay, d square equals to minus k square. Okay, so your d again is just plus minus I k, then your solutions of phi will be in terms of sine kx plus cos kx. Okay, of course you have some of the constant that you need to determine. Okay, so eventually you can write the solutions. Alright, so the solutions for your big psi now is just phi x t functions of time t. So this is none other than, so if I'm putting k, it's just k, so this k become 2me over h bar x, and then my cos become 2me over h bar x, and I have the another minus ie t over h bar. This will be your general solution for Schrodinger equation. Alright, so the rest is also the same. To the other PDE arise in physics also share the same concept. Alright, so you can look at there's discussions on wave equation, and the rest will involve others will involve a bit more complex differential equations, but some of them you will recognize in terms of Bessel function, okay, that you have learned before. So for this case, okay, it's the solutions of, you look at section 5 for those who are interested. Okay, looking at this steady state temperature in a cylinder. Okay, so if you look at the, you have a cylinder, differential equations in the cylinder coordinate. Okay, alright, and the best things and the solutions of this, okay, it's involve some things that you are recognized before. What is sine so look at how many variables over here. So your u now is a function of, so one can have r, multiplications of r, theta with theta, and then you have another one z with z. These are three one variable functions. Okay, Alright, so that's all. Cover up the PDE. Okay. So the concept should be workable on the rest of the PDE, but I'm not looking at the details of the finding solutions. Okay. Right. Thank you.